Hey everybody, it's Mr. Oliver. Today I'm going to do a brief overview of the solutions to the Unit 1 Fluid Mechanics practice for AP Physics 2. So maybe get that out and run through these solutions as you watch the video. Remember, you can pause, skip around, do whatever you need to do, and let's get started. Okay, so this first question asks about density, and so in this case we've got some kind of a sphere. So some kind of a shape that's got some liquid filled in it, and the density of the liquid is rho. So it says that we're going to enlarge the sphere to a bigger container and fill it completely with the same liquid. So the thing is that because it's the same liquid and it still has the same material in here, the density is going to stay the same. So the density of the large sphere is exactly the same the density of the same sphere, because the only thing that would change density, if you remember, is mass and volume. And since the density is increased, but I've also increased the mass by the same amount by completely filling it, that density would stay the same. So there's no difference. Now, on the second question, we've got a box and it's sitting on a disc. And so like if I looked at a top view of this, there'd be this box sitting on some kind of a round disc, and it exerts an average pressure on the wood. Now pressure, if you remember, is force divided by area. So in this case, what we're going to do is we're not going to change the force because the box is going to be the same, but we're going to put the same box on a smaller sheet of wood, a smaller circular. And what's happening is the diameter goes down by half. Excuse me. So what we need to do is say, well, if I make this area smaller, what happens to the pressure? So if you remember, area of a circle is pi d squared over 4, or pi r squared, pi times the radius squared. And so what happens is, if I change this area by 1/4 as much, this diameter, because that's goes down by, or I'm sorry, we're going to change the diameter by half as much. Because the diameter is squared, it means the area is going to go down by 4 times as much. So the idea is that this area here has decreased by 1/4 of what the original one was. And so if I decrease the area by 1/4, if this denominator decreases by 4 times, that means the pressure increases by 4 times. So our new pressure is going to be 4 times the original pressure. Now in this example, we've got a cylinder that's covered with a lid. And so I've got this cylinder, and it's got some airtight seal on this little lid that's on top of it. And it says that there's pressure in the room where this thing is sitting in. So that means that the air pressure pushing down on top of this lid is just regular atmospheric pressure, 101,000 pascals. That's what a Newton per meter squared is a pascal. And inside, the pressure is 0.41 times 10 to the fifth, or 41,000 pascals. So that means that between the inside, and remember the inside pressure is everywhere, so that also means that there's an upward pressure of 41,000 pascals pushing up on that lid. So the net pressure acting on that lid is going to be 60,000 pascals pushing down on the lid. So what we need to do, the question asks, if given a certain size and weight of the lid, we need to figure out how much force is required to lift that lid off of that cylinder. So if I look at a free body diagram of that lid, I'm going to have the weight of the lid, which is 200 newtons, pulling down. I'm also going to have this net 60,000 units of pressure that pulls down on it. And we'll calculate that here in a minute, the force due to the pressure. And so what we need to know is how much lifting force do we have to overcome these two. So the only thing that's left is say, well, this lifting force has to be at least equal to these two things combined. So the lifting force, F lift, is going to be 200 plus the force that this pressure gives. Well, if I take my pressure equals force over area equation, rearrange and solve for force, that force is going to be the pressure times the area. This term right here is going to be equal to the pressure force. And so when I plug those numbers in, I'll have 200 plus, come back down here, pressure, which is 60,000, times the area, which is pi r squared, so pi times 0.2 squared. And so when you do 200 plus these numbers, you end up getting a lifting force of 7736 newtons, or thereabouts. I can't remember if I rounded off on the air pressure term or not, but that'd be how much force you'd have required to lift that lid. Now this question down here talks about one container that has, it's a rectangular prism. So one dimension here, we call that an X dimension, is really tall. Y is a little bit shorter. So from here to here, that's a little bit smaller dimension. And then the Z dimension is really short. And so which orientation will the pressure at the bottom of the box be greatest? Well, you need to conclude that that's X. Because if you remember, pressure is related to the depth or the height at which the liquid would be filled. So if I filled this box completely up with the liquid, I would need to know how much of liquid is above that bottom surface. And so if you remember, we got an equation for hydrostatic pressure. P2 is equal to P1 plus rho GH, where H is that depth or that height of that fluid that's filling up that container. Pressure 1 typically is whatever pressure is being pushed on top of it. So that would be like an atmospheric pressure. And because that atmospheric pressure is the same in all three cases, you wouldn't consider that as being a factor. All right, moving on to the next page. I've got a problem, a manometer problem. And so with manometers, you really don't care about what happens down here in this little U-shaped part. You only care about what happens on these two vertical pieces. And it's real simple breakdown because right here, this little interface, if you remember, we'll call that an interface, where those two fluids kind of balance out. The idea is that both of these pressures down here at the bottom would be equal to each other. So if I said the pressure of A due to this oil and the pressure of B due to this water, those two things have to be the same. And the reason why they have to be the same is because that height is the same on both of them. So for right here, we just say that pressure A is equal to pressure B. Now pressure A at this location down here at the bottom would be the atmospheric pressure, which comes in from the top, plus the pressure due to all this fluid, which would be rho, the density of the fluid, times G, times this height. In this case, it's 27.2 centimeters. And then on the right-hand side, pressure B would be the atmospheric pressure, which comes in from the top, plus that rho GH term as well, where in this case H is 24.5. And so that atmospheric pressure being the same on both sides of the equation means these two terms cancel. You're also going to have the G term cancel because that goes away. And so what you're left with is that the density on the left-hand side, this would be the oil density, times 27.2 is equal to the density on the right, which would be the water density, times 24.5. And so we're trying to calculate the density of the oil. So the way we do that is just solve for density of the oil. And the reason why I didn't convert the centimeters to meters is because those terms would just cancel anyway. The units don't matter. All we're dealing with is this little ratio here. So do that calculation. Density of water, of course, is 1,000. So density of the oil would be about 900. 900 and change, 0.735 kilograms per cubic meter. And so when you see these manometer problems where you have an equal height between the two fluids, it's real simple. Just set it up to where you've got that little proportion, this little ratio proportion of densities and heights. All right. For the previous problem, calculate the absolute pressure at B. Okay, now absolute pressure, if you look at your equation again, P2 is equal to P1 plus rho GH. Absolute pressure typically is this P2 number. All right, so whenever we're trying to calculate that, we need to include the atmosphere. Now, if I said, what is gauge pressure? Gauge pressure would be the difference between the two. This would be a gauge pressure. So if I move that P1 term over to the left, that's a gauge pressure. So absolute pressure for this particular problem up here, P absolute would just be P atmosphere plus rho GH of the water is what we're trying to find. So that's 101,300 is atmospheric pressure plus 1,000 times 9.81 times 0.245. And you end up getting 103,703.45 pascals. All right, this next problem is kind of interesting. You've got a block of stone lowered by a crane into the ocean. So the idea here is you've got some kind of a crane sitting here on the shore, I guess. Maybe they're shoring up the thing. And we're going to lower this block down into the water. And what it wants is to sketch a graph that best describes the gauge pressure on the bottom of this block as a function of time. Well, gauge pressure, remember, is the difference between the two. So the atmospheric pressure would be P1, that'd be up here, and then P2 would be the pressure at whatever depth the block is, P2. And so they're trying to figure out the difference between these two. Well, if I take that equation, P2 minus P1, the gauge pressure, P-G-A-U-G-E, is equal to rho GH. So density, for all intents and purposes, stays the same as you go down to the ocean. G stays the same, and so the only thing that changes is H. So if you're descending at a steady rate, then that means that that H term, however far down you are, changes at a steady rate. In other words, that's a linear relationship. So what you would say is that the gauge pressure is proportional to the height. And so the deeper you go at a particular steady rate, the more pressure you have. And if you ever have a nice little one-to-one proportion like this, you're just plotting a linear function. Now, if it said that the block was accelerating down towards the bottom of the water, then of course you'd have to have some kind of an accelerating curve, in other words, some kind of parabola. Okay. Pascal's principle, this is a little multiple choice question. Let's go through all these. Let's start at the bottom. Viscous fluid flow, that has to do with friction. And when we're talking about Pascal's principle, we always assume it's frictionless, meaning that the factors that influence how, fluid is moving through the system is that it's frictionless. So if there's any kind of frictional effect, we can't choose that as an option. All right. Question D. This is true for a gas, but we're talking about fluids. In particular, Pascal's principle has to do with a fluid that's contained, that's a liquid, not a gas. So this is specific to liquids, not gases. And so if you remember that kind of little piston cylinder arrangement where the fluid is trapped inside here, hydraulic principle that we're talking about, we can't use anything that has to do with gases when we're talking about Pascal's principle. C is incorrect because a fluid technically includes gases, and gases are compressible, liquids are not, so we can't choose option C. Now, once again, here's another question that talks about viscosity. That is a true statement. The force required is proportional to its viscosity, but it doesn't work with a Pascal's principle because viscous things are a frictional effect. And so what we're left with is part A, or choice A. Pressure is transmitted equally in all directions. So if I increase the pressure at one point in the fluid, then everywhere in that fluid, that pressure is going to be also increased. That's Pascal's principle. And so along with that, here's a little example where we use Pascal's principle. The idea is that if I have this piston cylinder kind of arrangement, and I put some kind of a force up here at the top, where this area would be a small area, then the output amount of force would be magnified because this area over here is bigger. That's the idea. But Pascal's principle says that the pressures are the same, so pressure 1 has to equal pressure 2. And if I replace pressure with force over area, we can plug our numbers into this from this equation, from this information down here, and solve for force number 2. And that ends up being 10,000 newtons. Now, in this case, you don't have to convert the areas because they're in the same units. And what will end up happening is that they'll cancel. Like when I rearrange this, you get force 2 is equal to force 1 times A2 over A1. And those centimeter squared terms just cancel, so it doesn't really matter. Right, moving on to buoyant force. I would say that if there's anything to study for an AP exam, buoyant force is probably the number one. It shows up more than anything else. So definitely go back and spend some time looking through buoyant force, Archimedes principle. That's definitely the focus of the fluids unit. So on this question it says, which of the forces, if either, is greater? Well, they're both the same. Because in both scenarios, whether it's the ice here or a liquid here, this boat is not moving. It's in stable equilibrium. So you'd say the force of gravity pulling down on that boat has to be balanced by, in this case, the ice force or the normal force due to the ice. In this case, force of gravity hasn't changed. So that means that the buoyant force still has to keep it in equilibrium. It sinks a little lower, but who cares? We're just talking about the forces and whether they're different. Well, in this case, they're both the same because they're both in equilibrium. All right, here's an Archimedes principle problem. It says, how does the buoyant force compare to the block's weight? So what you need to do on Archimedes problems is start off with a free body diagram. So let's draw a box that represents this box. There is a buoyant force that pushes up. Now this little string right here is holding it in place, otherwise it's just going to float up to the top. So that means that there's a force of tension force pulling down, and also the weight of the object itself, W. So those two forces combined have to equal the buoyant force to be in equilibrium. So you say the buoyant force is equal to the tension and the weight. So looking at this, it's clear that the buoyant force is going to be bigger than either one of these. They're both smaller than the buoyant force. Specifically, the buoyant force is greater than the weight. That's what the question asks. How does the buoyant force compare to the block's weight? All right. This next one, this multiple choice question here. Let's just kind of go through these. the fact that the cube is completely submerged is evidence that the density of the cube is greater than the density of the fluid. That's false, because if you remember when we did our little fluid separation video, the less dense things float. So if this was true, then that block would sink. But in this case, it's being suspended in place by that string, because it wants to float up. So it can't be A. Kind of along the same lines, less dense things always float. It's really the string that keeps it submerged, not the density of the cube. Question C, if the density of the cube is greater than the fluid, it sinks. It's asking like the same thing over and over and over. So it can't be that. So therefore, the fact that there's tension in the string is evidence that the density of the cube is less than the density of the fluid. So anytime you have these fluids with a floating object, some object that wants to float up, be it a bubble or a box or a ping pong ball or whatever, just means that the density of this object is less than the density of the fluid, not the other way around. All right, this next question is a little tricky, so let me kind of walk through this and I'll show you exactly what you need to do to work this one out. All right, so what we've got is we've got a 1 cubic meter object floating with 20% of its volume above the water line. What does this object weigh out of the water? The density of the water is 1,000. So here's how we need to work it out. Let's start off with a free body diagram and sketch out what we have. We've got a buoyant force going up, tension going down, tension pulling it down. I'm sorry, is that the right one? Yeah. Oh, I'm sorry, we're talking about the previous problem, derive an expression for the density of the cube, not this one. So we're doing the same problem from the previous one here, right here, and we're trying to find out what the density of that cube is. Okay, so let's go through that. Oops. Okay, so here's our free body diagram from before. Buoyant force up, tension force down, the force of gravity, otherwise known as the weight pulling down. And so if I write a net force equation for this, I'm going to get the buoyant force has to equal the force of gravity plus the tension. We already showed that. So I'm going to call that equation 1. Now, my second equation is Archimedes' principle. Archimedes' principle says that the buoyant force is always going to be equal to the fluid density times the volume displaced times g. Well, in that previous example, the volume displaced was the entire volume because it was completely submerged. So we've already got that. The density of the fluid was the density of the water. Of course, we know what g is. So what we're going to do is we're going to set these two equations equal to each other. They're just two things that tell us the same thing. So I'm going to say set equation 1 equal to equation 2. And so we're going to get the force of gravity of the cube, that's the weight of the cube, plus the tension has to equal the density of the fluid times the volume displaced times g. Now, force of gravity is just mg, the weight, plus T is equal to density of the fluid times the volume displaced times g. The volume displaced is just going to be, since it's a cube of side length s, the volume will be s cubed. The tension is just going to be some variable that we got to kind of carry around. Now, the mass over here, this is the mass of the cube. So if you remember, mass is equal to the density times the volume. So the mass of this cube is the density of the cube times the volume of the cube. So this is where we pick up our density term that we're trying to find. So make one more substitution. The volume of the cube is s cubed, rho c. So I'm going to substitute this term in for my mass right here, because that's the mass of the cube. So we're going to have rho c s cubed g. And so all I need to do is take this equation right here, do some algebra, and solve for the density of the cube, rho c. Now I think you can do the algebra yourself when we go through this. We'll move the t over, divide by s cubed, and so we get density of the cube is rho of the fluid times volume cubed times g minus the tension divided by s cubed g. And so we derived a formula for the density. As long as I can measure this stuff, then I can get its cube density. All right. And so now let's move on to the floating cube, or the floating object in the water. So in this case, kind of a similar scenario, but if you go back into your notes or my notes on Canvas, I kind of show you how to address this. So in this case, whatever fluid we're floating in has a density. In this case, it's water. So it's 1,000 kilograms per cubic meter. This box, or whatever it is, whatever object is, it says that 20% is above the water line. So that means that 80% of it is below the water line. Now, because it is floating, that's a special case of Archimedes' principle, because the weight of the object has to equal the buoyant force. Because otherwise, if the buoyant force were too much, it would just float off into space. And if the force of gravity was too much, it would just sink down to the bottom of the water. Now, it does tell us what the volume of this cube is. It says the volume of the object is just 1 cubic meter. And so to start this off, because it is floating, you say that the buoyant force is equal to the force of gravity. Now, buoyant force is rho vg, or rho is the density of the fluid. The volume here is not the entire volume, it's only the volume that's displaced. It's this volume right here. The displaced volume. Now over here on the right hand side, force of gravity is just mg, so it's nice, get rid of a g term. And so that means that the mass of this object is equal to the density of the fluid times the volume displaced. Well, the volume displaced is 80% of the total volume. So 0.8 times the total volume. And so that means that the mass has to be 1,000 times 0.8 times the total volume, which is 1. And so that means the mass of this object is 800 kilograms. And so the question says, what is the weight of the object out of the water? Well, the weight is just mg. So it's going to be 800 times 9.81, which is 7848 kilograms. And guys, this question right here, I went back and looked at all the practice tests and the kind of released exams and other things that I've seen on the fluid mechanics. This kind of question showed up way more than anything else. I've seen that, there were some other types of fluid mechanics questions, but a floating object Archimedes style problem shows up a bunch. So spend some good time looking at this. All right. So we're almost done. We've got a couple pages left. Continuity. The continuity is an expression of conservation of mass, and it just says that A1 times V1 has to equal A2 times V2. All right. So what it's saying, or not V2, not V squared. So what it's saying is that whatever amount of fluid comes in on one side has to be conserved by coming out at the other side of equal amounts. We call it the volume flow rate. If you remember Q dot, Q dot, Q dot. How much fluid comes in has to be the same amount of fluid coming out. And we express it with continuity. And so that's a pretty straightforward thing. Let's calculate our areas first. Area 1 is pi d squared over 4. when we plug our numbers in, diameters and stuff, we end up getting 2.011 square millimeters. And once again, I'm not converting because I know eventually that term's going to cancel out because of this one-to-one relationship here. Area 2, we do the same thing and you get 0.251 square millimeters. And so then when you take your continuity equation and solve for V2, we'll call the exit velocity V2. And they're going to be the same. V2 is going to be, I'm sorry. Back here on area 2, we need to actually multiply this number by 2. The individual ones was like 0.125, something like that. So this is actually the total area of both of these combined. Sorry about that. And so then velocity 2 is A1 times the first velocity divided by the second area. And you plug your numbers in and you get 8.012 times the original velocity. So it's about 8 times as fast coming out. All right. Okay, so here we've got this is a Bernoulli style problem, Bernoulli's equation. I'm going to do this on a separate sheet of paper so you can see everything. The problem is pretty straightforward. We just got to do a little bit of setup. So let's just kind of list things that we know from the problem. We know that the velocity right here at the beginning, we'll call this V1, is 9. So V1 is equal to 9 meters per second. We can calculate area 1. It's going to be 10 centimeters in diameter. So we'll do pi d squared over 4. So it's going to be pi times, we'll just call that d1 for now, d1 squared over 4. I'll show you why here in a minute. So this is d1. Area 2 is going to be pi d2 squared over 4. Call this d2. And so the first thing we need to do is we actually need to find the exit velocity, V2. So we're going to use continuity again. V2 will be A1 over A2 times V1, using the same equation we did before. And the reason why I didn't go ahead and calculate this is because when I set up this ratio, the pi terms, as well as the 4 terms, this 4 and this 4 and this pi cancel. And so what you end up getting, V2 is just d1 squared over d2 squared times V1. And so that's 10 squared over 30 squared times 9. And so the exit velocity is 1 meter per second. Oops, sorry. That's our exit velocity. And so now in our second step, we just use Bernoulli. So PA plus rho G, the height of A, plus 1/2 rho V of A squared has to equal pressure at B plus rho G Y at B plus 1/2 rho V at B squared. And so some of these terms can cancel. We'll assume it starts on the ground level, so the height of A is 0. And I guess that's all that we can cancel. So what we're looking for is the pressure at B. So pressure at A, it tells us, is 200,000 plus 1/2, and it's water, so it's 1,000. The density is 1,000 times 9 squared. Has to equal the pressure at B plus 1,000 times 9.81 times Y at B. So that's how high that exit is. I'm thinking this one is 8 meters. plus 1/2 times 1,000 times 1 squared, which is just 1. And so now you just go through, take some time and calculate this out, and pressure at B is about 161,520 pascals, depending on rounding and stuff. And that's your Bernoulli question. Bernoulli kind of questions are probably the second most common. Usually, though, they don't ask you to go in and calculate anything like this, but this is one exception. All right. Now, this next question is essentially a Bernoulli style equation as well, or question as well. It's just specific to, remember Torricelli's theorem? That's what this question's asking. Basically, it's a conservation of energy where the higher the water level, the faster the water comes out of this. And what it's doing is it's saying, hey, if I have these water outlets coming out, they're going to hit the ground at some distance away, d, that's what they're talking about. And the idea is that the faster the water goes, the further out it'll shoot. And if you just remember, the higher the water level, the more potential energy it has. And so that potential energy, due to gravity, is going to convert into something else, and it's going to convert into kinetic energy at the bottom. And so the more height you have, the more speed you're going to have. In other words, the distance that this water comes out is going to be proportional to the height of the water level. More height, faster velocity, farther it shoots out. And that's even true even if you have something like this, where you've got a tank of water or something like that, and you have an outlet at the bottom, and maybe you've got a little valve, like a little fountain or something, with a little nozzle, that as this water has some kind of elevation above this exit height, the height of that water is going to be proportional to this height. All right, last question. So this last question is just kind of a conceptual question asking about Bernoulli again. And so the only two true statements are going to be A and C. The pressure tends to increase due to the decrease in fluid speed. Well, that's true, but it doesn't have to do with talking about pressure of the fluid. Speed increases due to continuity. And then down here at D, it's a pressure-depth relationship. The further down you go, the pressure increases. And so what we're left with is the pressure tends to decrease due to the increase in fluid speed. The faster the fluid moves, the less pressure you have. And so this is just trying to trick you. You got two things that sound pretty close. You just got to make sure you're right. All right. And I think that just about does it. All right. So if you'll come Zoom, ask me any questions you have when we meet on Wednesday at 1. Let me make sure I get the time right. Our meeting is scheduled for 1:15 Wednesday, April 1st. So if you want to come watch that, ask questions, we'll go through the free response questions I assigned as well. So thanks, guys, and I'll see you next time.